Greetings, mathletes, and welcome back to the channel. In today's lesson, we're going to be learning about geometric series and telescoping series. But before we do those, I still need to introduce the idea of a series. What's an infinite series? So we're not talking about a television series, but it is kind of like a television series in that a television series has episode after episode after episode. But in math, an infinite series is something somewhat different, but it's kind of the same idea in a way. So an infinite series is a sequence of partial sums. Okay? It's a sequence of partial sums. And what that means is, remember, a sequence just has term after term of the sequence, and it starts at usually on the first term, then the second term, then the third term. So make sure you've already watched my video on infinite sequences before you look at this video. But it's a sequence of partial sums. And probably the easiest way to learn about them is by example. But the basic idea is, with a sequence, you can have, for example, your sequence can be 2, 4, 6, 8, 12, 10, 12, whatever. You can have a sequence like that, but in a series, you're going to be adding up all of the previous terms as you go to the next term. So instead of being 2, 4, 6, 8, 10, 12, you would have 2, and then you would have 2 plus 4 is 6, and then you would have 6 plus 6 is 12, and then you would have 8 plus 12 would be 20. So you're actually going to be adding things up each time you add a new term. So it's a sequence of partial sums, and remember that the word sum means add. Okay, so you add up all terms to that point. Okay, that's what a sequence of partial sums means. But like I said, it'll make a lot more sense when we actually do an example. Okay, so let's jump into an example here. Okay, example. Write out the first few terms of the series. Write out the first few terms of the series. Okay. That's the first thing they ask us to do. Write out the first few terms of the series. And then they're going to ask us, what is the series sum? What is the series sum? Remember, the word sum actually means add. Okay? So if they ask us to find the series sum, that means we need to add up all of the terms, but it's an infinite series, so it goes on forever. Okay, and for this example, we're going to be doing the sum from n equals 0 to infinity of -1 to the n over 3 to the n. So the way we know this is a series and not a sequence is it actually has this big thing that looks like kind of like an E, but not quite. This is called sigma. Okay, this is called sigma notation, and hopefully you've seen it in another class, like in Calculus 1 maybe. But this here is sigma notation. Okay. Sigma notation. And sigma notation basically just means you add up everything, like we were saying. Okay, so what are the first few terms of the series going to look like? Well, you just plug in different values. So the first term is going to be where n equals 0. So if n equals 0, then we're just going to have, the first term is going to be negative 1 to the 0 over 3 to the 0. Okay, so all I'm doing there is I'm plugging in n equals 0 over here. So we have negative 1 to the 0 over 3 to the 0. And remember, any number to the 0 is 1. Okay, so this is going to be 1 over 1, which is 1. Okay. And so that's going to be the first term. Okay, so this one that we just calculated right here, this one is the first term. Okay, and then from here, how do we calculate the second term? Well, if this were just a sequence, then the second term would be where we plug in n equals 1, and then whatever we plugged in after we evaluated it, that would be our second term. But because of this sigma notation, because this is a series, we actually have to add them up. So notice it asks us to write the first few terms of the series, but like I said, a series is a sequence of partial sums, which means instead of just plugging in the numbers, you're actually going to be adding up all of the values up to that point. That's why they're called partial sums, because you have the partial number of terms there. Okay, so all the terms up to that point. So when n equals 1, because we're adding them up, it's actually going to have the first term, which we already calculated, which is negative 1 to the 0 over 3 to the 0, plus the second term, which is negative 1 to the 1 over 3 to the 1. Okay? And we already did negative 1 to the 0 over 3 to the 0. We know that that one is 1. And then for the second one, we have negative 1 over 3. So we have plus negative 1/3. Okay, so we have 1 plus negative 1/3. All right, and then what's 1 plus negative 1/3? Well, 1 minus 1/3 is 2/3. Okay, so our second term is going to be 2/3. Okay. All right, and so what we got there is 2/3, and so that's going to be our second term. And then let's see. So this can get a little bit confusing. I had to pause for a second to think about this, but so what I'm actually showing you here is this isn't actually the second term. This is actually the second partial sum. So this can get a little bit confusing. So the 2/3 is called a partial sum. So that one's called a partial sum. But the second term is actually just the same as the second term of the sequence. So I might have misspoken there a little bit. So that's why I had to pause it and kind of refresh my memory. But what I meant to say is the first term is still 1, but the second term is actually going to be just this right here. Okay, so this one right here, this negative 1/3 is the second term. Okay, so the second term is going to be negative 1/3. And what I calculated here is actually the partial sum. So that's where you add up the first two terms. I'm sorry, I got it a bit confused, but hopefully it's understandable now. But that's nice because actually for your homework, they don't really ask you to do the partial sums. So what I did here was kind of unnecessary. So all we really had to do was calculate the negative 1/3. So I made it harder than it needed to be. Okay, so, but that's how we do partial sums if you ever have to do them in another class. But for our terms, when n equals 1, the second term is going to be negative 1/3. And they want us to write out the first few terms, so let's do n equals 2. So we're not going to do the partial sum this time, we're just going to plug in. So when n equals 2, the third term is going to be negative 1 to the 2 over 3 to the 2. Okay, so we're going to have negative 1 squared over 3 squared. So that's going to be 1 over 9. And this one right here is our third term. Okay, this one's our third term. And I think for these, they usually have you go up to the fourth term. So let's go ahead and do the fourth term. Okay, so when n equals 3, that's actually our fourth term. And remember, it's our fourth term because we started on n equals 0. So n equals 0 is the first term, n equals 1 is the second term, and so forth. Okay, so when n equals 3, we're plugging in 3. So we have negative 1 to the third divided by 3 to the third. So remember, negative 1 raised to an odd power is negative, and negative 1 raised to an even power is always positive. So this one's going to be negative 1 over 3 cubed. And for 3 cubed, that's going to be 3 times 3 is 9, times 3 is 27. So we're going to have negative 1 over 27. And we can just go ahead and factor that minus out front. So we get negative 1 over 27 for the fourth term. So since the way I said it at the beginning was a little bit confusing, I just want to make sure that you're solid on the difference between a partial sum and the actual terms. Okay? So let's talk about that. So the partial sum is the sum of all terms up to that point. Okay, so for the partial sum, when n equals 3, okay, so when n equals 3 here, the partial sum is going to be the sum of all the terms up to that point. So, oops, what did I do there? The sum of all the terms up to that point. So that's going to be 1 plus negative 1/3 plus 1/9 plus negative 1 over 27. Okay. So 1 plus negative 1/3 plus 1/9 plus negative 1 over 27. The partial sum is what's written right there. And then each of those numbers in the partial sum, those are called the terms. Those are called the terms of the series. Okay, so each of these, the 1, the negative 1/3, the 1/9, the negative 1 over 27, those are called the terms. Okay, so hopefully it's clear now what everything is called so we understand it. So like for here, if we wanted to calculate the partial sum, we could build these to a common denominator, or we could just use a calculator, either way. But I'm not going to bother to do it because it's just basic arithmetic. Okay, but the partial sum would be the sum of all of these. All right. Now, how do you find the sum of the entire infinite series? Well, you have to know what kind of series it is. So now when we look at the terms of this series, 1, negative 1/3, 1/9, negative 1 over 27, what is happening with each of these terms? So what's going on here? Well, we're looking for a pattern. So let's write the pattern down here. So the pattern Well, actually, they already gave us a formula for the pattern, so we won't have to really look at it that much. But one thing we're going to look for is what kind of series is this? So they give us the formula here, and it's the sum of -1 to the n over 3 to the n. Okay, so sum of -1 to the n over 3 to the n. So they give you a formula for it, but we need to write it in a certain way because this is actually going to be what's called a geometric series. So the way we're going to write it is instead of -1 to the n over 3 to the n, we're going to rewrite it as -1/3 quantity to the n. And that's n equals 0 to infinity. So they gave us this first formula right at the beginning of the problem, so we didn't have to figure it out on our own. Okay, but then why did I rewrite it this way? Well, I'm trying to rewrite it in the form of what's called a geometric series. Okay, so to rewrite it as a geometric series, you need to write it in the form the sum of AR to the n. Okay, so we're learning about a geometric series here. So a geometric series, these are actually one of the most common kinds of series, by the way. A geometric series can be written in the form sum of A times R to the n. Okay? Sum of A times R to the n, where A and R are constants. Okay, so sum of A R to the n, where A and R are constants. And the reason I'm pointing the arrow at this one is the one that we have here is actually a geometric series. Okay? And so if it's in that format, then that means it's a geometric series. So we can see that it actually is in this format. There's not really an A here, but we can just write in a 1 there. Okay, so we can write the sum of 1 times -1/3 to the n. Okay, and that's actually the format of a geometric series. Now, what can we do with this? Well, it turns out that if it's a geometric series, there's actually a nice formula for calculating the value of the formula's sum. Okay, but the series only converges if the absolute value of R is less than 1. So that's an important thing to know. Okay, so a geometric series converges. Okay, so the series converges if the absolute value of R is less than 1. Okay. If R is greater than or equal to 1, then that might mean that the series diverges. Okay, but I don't need to write that. The important part is we know the series converges if the absolute value of R is less than 1. Okay, so so here we can see that A is going to be 1. Okay, so looking at this series we have here, A equals 1. That's this right here. And then we can see that R is actually equal to -1/3, which is right here. Okay? So since R equals -1/3, And then we have the absolute value of r is absolute value of negative 1/3. That's equal to positive 1/3, which is less than 1. Well, that means the absolute value of r is less than 1, which means this series converges. And you might be wondering, well, okay, it converges, but how do we figure out what it converges to? Because remember, if something converges, that means that the series or the sequence, when you consider everything, it goes to a specific number. Okay, so it's going to be a real number. It's not going to be infinity or negative infinity. So this series needs to converge to a real number, and it turns out if it's a geometric series, then it converges to a over 1 minus r. Okay? So for a geometric series, that converges, the value of the sum, and the sum means actually the sum of all the terms in the infinite geometric series, is actually written as S equals A over 1 minus R. Okay? So S here stands for sum. So S equals A over 1 minus R. All right, and that's just a nice little formula here, because all you have to do is figure out what A and R are, and then you plug them in. So in this problem, A is 1, R is negative 1/3, and we just need to plug those in. Okay, so like in this problem, S is going to equal A, which we said was 1, over 1 minus R. So that's going to be 1 minus negative 1/3. Okay, so that's going to be 1 over 1 plus 1/3, right, because the minuses cancel. And then 1 plus 1/3 is 4/3. So we have 1 over 4/3, which is equal to 3/4, right, because if you divide by a fraction, that's the same as multiplying by the reciprocal. Okay, so we got our S. Our S equals 3/4. And that's actually the sum of the series. So what does it mean to be the sum of the series? That means if you add them up all the way up to infinity, actually the sum of all those terms going all the way to infinity is actually 3/4. Okay, so the series sum, which means the sum of all of those terms, is, so the sum from n equals 0 to infinity, of negative 1 to the n over 3 to the n is actually equal to 3/4. That whole thing, adding up all the terms going all the way up to infinity, is going to be 3/4. And that's the nice thing about geometric series, is not only are they really common in applications in science, but they're also pretty easy to work with. Because it turns out that once you know it's a geometric series, once you can write it, if you can write it in the form the sum of A times R to the n, and then you can identify what A and R are, then you know whether it converges or not, and you can just plug into this formula, which is an easy formula for calculating the sum. Okay? So cool. So that's our first example. All right, and then I think I wanted to take a look at another one. Well, a few more actually. Okay, so let's do example number 2. Example number 2 is the sum from n equals 0 to infinity of 4 over 3 to the n plus 1 over 5 to the n. So for writing out the first few terms of the series, rather than having to write n equals 0, n equals 1, all that, I'm just going to go ahead and write them all out and just write pluses between them, because that's really what the sigma notation means, the summation notation. So the first term is where n equals 0. And if n equals 0, then we're going to have 4 over 3 to the 0 plus 1 over 5 to the 0. Okay, but that's just going to be 4 over 1 plus 1 over 5. Not 1 over 5, 1 over 1, my bad. Because 5 to the 0 is 1. So it's going to be 4 over 1 plus 1 over 1. But remember, any number over 1 is just a number. So that's actually just going to be 4 plus 1. So our first term is actually just going to be 4 plus 1. That's where n equals 0. And then we're going to be adding these terms. Okay, so when n equals 1, I'm going to write that over here. So for that next term, we're going to have 4 over 3 to the 1 plus 1 over 5 to the 1. Okay, so we're going to have plus, that's going to be 4/3 plus 1/5. Unfortunately, on your homework on this problem, they don't make you combine all these fractions, which is just nice. It's going to be multiple choice, and you just have to choose the one that looks correct. Okay, and then our next term is going to be where n equals 2. So when n equals 2, we're going to have plus 4 over 3 squared plus 1 over 5 squared. Okay, so that's going to be 4 over 9 plus 1 over 25. Okay, so kind of squeezing it in there. All right, so let me move this down a little bit so I can box that. I don't know why I boxed that, actually. I meant to put parentheses around it. Just having a senior moment here. Okay, so we've got 4/9 plus 1 over 25. And you can keep going, of course, but I think writing the first 3 terms should be good enough here. You might have to write 1 or 2 more for your homework, but I think we get the idea. Okay, so that's writing the first few terms. And then the other thing they asked us to do is to find the sum of the series. Okay, so how do we find the sum of the series? Well, you're going to notice that these two look kind of similar to the last problem. And your goal here is to rewrite each of these in a format where we can have them as a times r to the n. Okay, so what we're going to need to do here is, let me erase all this. So because we're learning about geometric series here, and these look like geometric series, our goal is to write each of them in the form sum of a times r to the n. Okay, so goal is write, some kids outside. Okay, so goal, write as the sum of a times r to the n. And of course the a and the r are going to be different for each of those terms. But it turns out that you can actually just distribute the summation symbol. So we can do that, and then each one is going to be a geometric series. Okay, so what we're going to do is, after we distribute the summation symbol, we're going to write each of them as the sum of a times r to the n. So for the first one, notice that the 4 doesn't have an n in it, so that's actually going to be factored out front. So we're going to write the first one as 4 times 1/3 to the n. Now, why am I allowed to write it as 1/3 to the n? Well, if you think about it, if I distribute that n to each of these exponents, in the numerator, 1 to the n is 1, and then in the denominator, 3 to the n is 3 to the n. So we have 4 times 1/3 to the n. Okay? And as you can see, that's in the format a times r to the n, where a is a constant and r is a constant. So we're good with the first one. And then for the second one, instead of writing it as 1 over 5 to the n, we're going to do the same thing we did over here. So we're going to write it as 1/5 with parentheses around it, raised to the nth power. Okay, so our other series here is going to be the sum from n equals 0 to infinity of 1 over 5 raised to the n. Okay, and now that these are both geometric series, we can go ahead and calculate each of their sums separately, and then we'll add them up. Okay, and even though there's two of them, each one is a geometric series. So for each one, we're going to need to label what A and R are, and then we'll plug them into the formula. Okay, so for this first one, we can see that A equals 4 and R equals 1/3. Okay, and since the absolute value of R equals the absolute value of 1/3, which equals just positive 1/3, because remember, absolute value is always positive. And this is less than 1. That means it converges. The series converges. And it converges to the sum S equals A over 1 minus R. S equals A over 1 minus R. Okay, so what's that going to look like here? Well, we're going to have, for this first sum, we're going to have S equals A, which is 4, over 1 minus R, so that's 1 minus 1/3. Okay, so that's going to be 4 over 2/3. 4 over 2/3. And if you're dividing by 2/3, that's the same as multiplying by the reciprocal. So if I flip over 2/3, it's going to become 3/2. Okay, so we have S equals 4 times 3/2. So the 2 and the 4 cancel out, and we get a 2 on the top, so we get 2 times 3 is 6. So the sum of the first series is actually just 6. Right, because if you do 4 divided by 2/3, that's 4 times 3/2. 2's cancel out, you get 2 times 3 on the top, which is 6. Okay, so that's good. So this first sum here is 6. Okay, and then for the second sum, I'm going to use a different color so we don't get them confused. For this second sum here, I'll do that one in green. For that one, we can see there's no A, so that means A is 1. So A equals 1, R equals 1/5. Okay, and the absolute value of 1/5 is 1/5, which is less than 1. So that means the series converges, and its sum, or what it converges to, is A over 1 minus R. Okay, A over 1 minus R. So that's going to be our S, or our sum. Okay, so plugging in here, A is 1, and then R is 1/5. So we have 1 over 1 minus 1/5, which is 1 over 4/5. And of course, if we flip over 4/5, that ends up being 5/4. So flip this over and we get 5/4. Okay, so we get S equals 5 over 4. Okay, so what we have here is 6 for the first one, and then we have 5/4 for the second sum. So because they were added together over here, we're going to have 6 plus 5/4. 6 plus 5/4. Okay, and then for the 6, we can rewrite that as 6 over 1. And then we can combine these fractions. Okay, so instead of writing 6, I'm going to write 6 over 1. I can build them to a common denominator by multiplying the first one by 4 on the top and the bottom. So that's going to give us 6 times 4 is 24 over 4 plus 5 over 4. Okay, and 24 plus 5 is 29. So the series sum is actually going to be 29 over 4. So I'll box that. Okay, so the series converges and the series sum is 29 over 4. Or in some books they'll say the series converges to 29 over 4. I don't think our book says that though. Okay, and I think you should be pretty good for your first few problems now. Those are all pretty similar. Okay, so I think we're good for geometric series. So let's move on to the other topic in this video, which is telescoping series. And a telescoping series, I'm going to do again by example. So example, find a formula for the nth partial sum of the telescoping series. Find a formula for the nth partial sum of the telescoping series. And I know telescoping series sounds like you're doing astronomy with a telescope looking in the sky or something, but it's not actually that. It's just called telescoping because a bunch of terms cancel out. So it's sort of like as you look at all the terms, a bunch of stuff cancels out. So if you stretch it out far enough, you're going to end up with the first term and the last term, which is sort of like a telescope because it sort of stretches everything out, everything cancels out, and then you're really looking at the first and the last. So I think that's why it's called telescoping. Just the same way a telescope is long and you stretch it out and then it lets you zoom in on something. Okay? So that's the basic idea. So we want to find a formula for the nth partial sum, and then we want to use it to determine if the series converges or diverges. If the series converges, find its sum. So a lot of instructions here. Okay. Use it to determine whether the series converges or diverges. Okay. So find a formula for the nth partial sum of the telescoping series. Use it to determine whether the series converges or diverges. If it converges, find its sum. Okay, so that's a really long set of directions. So let's go over that again. Find a formula for the nth partial sum. Remember, partial sums are where you add up a certain number of terms, all the terms up to that point. You need to find the nth partial sum of the telescoping series. Again, we haven't talked about what a telescoping series is exactly, but basically it's where you have minuses and pluses and a bunch of stuff cancels out. All right, and then use it to determine whether the series converges or diverges. And that's going to be done just by taking a limit. And then if it converges, we find its sum. And these are really not so bad. So let's go ahead and dive into one. So for our first example, example number 1, our series is going to be the sum from n equals 1 to infinity. Okay, so this one goes from n equals 1 to infinity. The earlier ones went from 0 to infinity, but this one happens to start on 1. Okay, and this is the sum of 3 over n minus 3 over n plus 1. Okay, so we need to find a formula for the nth partial sum. So the way we write the nth partial sum, or at least the way I write it, and the way my math lab writes it, is instead of writing s, we actually write s with a subscript of n. So that subscript of n there means you're only writing out the first n terms. You're not going all the way to infinity, which would be if you just write s, that means the sum of the entire series going all the way from n equals 1 to infinity. Whereas s sub n is just going to be the first n terms, and then you add them up. Okay, and the way you want to do this is you want to start at n equals 1. So we're going to have 3 over 1 minus 3 over 1 plus 1, which is 3 over 2. And let me kind of move over here a little bit. So you can see we're doing this formula here, and we're starting at n equals 1. And then the next one is going to be, since we're adding them up, it's going to be plus 3 over 2 minus 3 over 2 plus 1, which is 3 over 3. Okay, and then we can keep going. So the next one's going to be 3 over 3 minus 3 over 4. And hopefully by now we're starting to see the pattern. So let me zoom out a little bit. So the next one's going to be 3 over 3 minus 3 over 4. Okay, and then we're going to have 3 over 4 minus 3 over 5 plus 3 over 5 minus 3 over 6 plus 3 over 6 minus 3 over 7. And I'm only going to write this many for the first problem. And then I'm going to write plus dot dot dot. And then we're going all the way up to n. So this is going to be plus 3 over n minus 3 over n plus 1. And if you think about it, what would the term right before that be? It would be 3 over n minus 1 minus 3 over n. So now, remember, you don't actually need all these parentheses because they're adding. So with each set of parentheses, because it's a sum, we're adding all those parentheses. And you might have already noticed something here. If you've been watching here, you might have noticed, well, we can simplify this a whole lot. And like I said, it's like a telescope, because if you look at the whole thing, it stretches it way out. But then if you look through the telescope, it lets you focus in on a single thing. So this is stretched way out, but a lot of stuff is going to cancel here. So you might have already noticed right at the beginning, we have a negative 3/2 and a positive 3/2. So those are the same thing, but they're opposites. So those cancel out. So those cancel out, and then the negative 3 over 3, the positive 3 over 3, those cancel out. The negative 3/4, positive 3/4, those cancel out. Negative 3/5, positive 3/5, negative 3/6, positive 3/6. And then since we see the pattern, we know all of these terms in the middle are going to cancel out. So I can cross out the dot dot dot. And we know that the 3 over n minus 1 had to cancel out with the previous term. And we can also see the negative 3 over n and the 3 over n are going to cancel out. So basically, it's all stretched out like a telescope, but all this stuff cancels out, and now we're just zoomed in on, really, there's only 2 terms left. And what are the 2 terms that are left? Well, we have a 3 over 1, which is 3, and then we have minus 3 over n plus 1, because everything else canceled out. So that's a telescoping series, and so what we found there was a formula for the nth partial sum. So s sub n equals 3 minus 3 over n plus 1. So I'll box that. That's the formula they were asking for the nth partial sum. Okay, and then they want us to determine whether the series converges or diverges. And with these, basically you can just take the limit as n goes to infinity of the nth partial sum. And if that's a number, that's what this series converges to. If it's infinity or negative infinity, then the series diverges. Okay? So we take the limit as n goes to infinity of s sub n, okay, of the nth partial sum, and that's going to be the limit as n goes to infinity of 3 minus 3 over n plus 1. Okay, and the limit as n goes to infinity of 3 is just 3. And then the limit as n goes to infinity of 3 over n plus 1. Well, the denominator is going to be going to infinity, but a fixed number over infinity is going to go to 0. Okay, so this second term, because the denominator is infinitely large, the second term is going to go to 0. Okay, so really we just have 3 minus 0, which is 3. And what we just found there, the limit of the partial sum is the same as the series sum. Okay, so what we say here is the series converges because we got a real number. Okay, we did not get infinity or negative infinity. So the series converges because the limit as n goes to infinity of s sub n is a real number. Okay, 3 is a real number. So this limit as n goes to infinity of s sub n, it turns out that if you find the limit as n goes to infinity of the partial sum, that's the same as the value of the sum of the whole series. Okay? Okay? So that means, and the series sum is 3. So if you can find a formula for the nth partial sum, then you take the limit as n goes to infinity of that. If that actually gives you a real number, then that means the series converges to that number, or the value of the series sum is that number. So it's pretty handy. Pretty cool, huh? So that's a telescoping series. And you have a few of those on your homework. Most of them are pretty straightforward, I think. So I think I'll probably just do one more. So we haven't seen any series that diverge, so let's take a look at another one, maybe one that might diverge. So this was, excuse me, this was example number 1. Let's take a look at example number 2. So example number 2, this is another telescoping series. And for this one, we have the sum from n equals 1 to infinity of ln of root n plus 1 minus ln of root n. Okay? So the sum from n equals 1 to infinity of ln times ln of root n plus 1 minus ln of root n. So again, what you want to do is you want to write out your s sub n. Okay, so your nth partial sum is going to be s sub n, and you start with n equals 1. So we have ln of root 1 plus 1 minus ln of root 1. Okay, that's going to be the first term. But remember, 1 plus 1 is 2. I think we all got that since we've gotten this far. And then the square root of 1 is 1. So we have minus ln of 1. And remember that e to the 0 is 1. So this minus ln of 1 is actually going to be 0. Okay? And then what's our next term going to look like? Well, it's going to be ln of root 2 plus 1, so that's going to be ln of root 3 minus ln of root 2. Okay? So for our next term, we have ln of root 3 minus ln of root 2. Okay? And then we have, for our next term after that, we're going to have ln of root 4 minus ln of root 3. And I think we see the pattern here. So we're going to write plus dot dot dot. And we're also going to notice that a bunch of stuff is canceling out here already. So what's canceling out? We have the ln of root 2's cancel out, the ln of root 3's cancel out, and if you wrote out more terms, the ln of root 4's are going to cancel out, the ln of root 5's, and so forth. And then when we get towards the end, to the nth partial sum, to the nth terms, you're going to have, well, let's see, our formula was ln of root n plus 1 minus ln of root n. And we can write the term before that by just going one less. So the term before that's going to be ln of root n minus ln of root n minus 1. Okay, that's the term before it. And then we have the nth term is going to be ln of root n plus 1 minus ln of root n. Okay, so we have plus ln of root n plus 1 minus ln of root n. And we know just from the pattern here that all these terms are going to cancel out. The negative ln of root n minus 1 is going to cancel out with the one before it. And then we can also see that the ln of root n cancels out with the negative ln of root n. Okay, and because the first term actually just had a 0 here, there's nothing for the first term. So all we really have left over here is ln of root n plus 1. This is all we have left. So the nth partial sum is actually going to be s sub n equals ln of root n plus 1. Okay, and then for that one, basically, there's our nth partial sum, so they asked for that. And then what do they want us to do with that? Well, they wanted to determine whether the series converges or diverges. And just like before, if we take the limit as n goes to infinity of the nth partial sum, that will tell us whether it converges or diverges. So the limit as n goes to infinity of s sub n, which is ln of root n plus 1, is going to basically give us ln of the square root of infinity. Square root of infinity is infinity, and ln of infinity is infinity. So this whole thing goes to infinity. Okay, so because the limit as n goes to infinity of s sub n isn't a real number, it's infinity, not a real number, that means the limit doesn't exist. Because infinity isn't actually a number. Infinity is forever. It's not actually a number. So the limit doesn't exist because the value of the limit's actually infinity. So what that means is the series diverges. So that's all we have to say. We just say the series diverges because the limit as n goes to infinity of s sub n does not exist. Okay? So that's cool. We got to see one that diverges. And then, you know, for this homework, all the ones with the geometric series, those ones all converge. But a geometric series can diverge, and I believe we'll see that in a later video and on a later homework. But that completes this lesson. So, thanks for watching, and keep your pencils sharp.